Shall I start or?
Yes, 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 Poonam, go ahead.
Okay.
Yeah.
Okay, so I'll be talking about anytime mining of data streams. Uh, so data streams, actually everybody I think knows that what is data streams: infinite sequence of objects, maybe d-dimensional, and data keeps on coming. And inter-arrival rate time may be denoted by delta t. It can be fixed, it can be variable. So most of the two basic constraints of mining data streams, limited time and limited memory. So limited time, so there is a speed of a data stream. So according to the speed, you get very little time to process the data points. And in that time only you need to process. So you need, you may not be able to fully process the data points and get the final result, like whatever task you are doing, for example, classification, clustering, or association rule mining. So you may end up, getting some intermediate representation of the data stream, and later on, maybe offline or maybe at some point of time when the query arrives for the final results, you process them again and get the final results. Limited memory, so you know that the memory is always limited. So we need to process our data points using that memory. So there is always a trade-off. If you want to if you want to enhance the efficiency, then you need more space mostly. And if you try to reduce this space, you need more time to process the data points. So intermediate representation actually sort of balance these two things, like whatever time is available and whatever space is available. According to that, you design your algorithms and have your representations, intermediate representations. And because of these two constraints, generally we design our algorithms which are single pass algorithms. Single pass algorithms means you will see the data points only once, and you process them and get the intermediate representation. Um, that means you process the data and throw the data after processing. You don't keep the data points stored somewhere. So you need single pass algorithms. Okay, so let me take some point. Okay. So these are the existing algorithms for classification, F5, clustering, anomaly detection, all popular tasks of mining. And all these algorithms are for streams, and they are actually budget algorithms. Budget algorithms are those algorithms which take a fixed amount of time to process a data point. So this the stream speed which they can handle is sort of fixed. So they can handle actually fixed maximum stream speed. So these algorithms cannot process higher speed streams because of the fact that they take more time to process a data point, and by that time the next data point will arrive, and so on. And there will be a queue of data points which will be waiting to be processed. Uh, so budget algorithms, they actually cannot utilize the fact that the real-time data streams they take actually they are arriving at a variable speed. For example, you take any example of which of application which generates the data streams. Maybe say stock market, or it is a retail data which you are getting. So rush hours, there will be more transactions, and the non-rush hours, there will be less number of transactions which will be arriving. Maybe you can take another example of tweet streams. So people, they are tweeting, there are hours where a lot of tweets you get, but there are some times where that speed may not be that high. So these budget algorithms, they actually do not bother actually or utilize this time, which is variable inter-arrival rate. So if the available time allowance is less than budget, you won't be able to produce results. And if the available time allowance is greater than budget, you sit idle. So if you're waiting for the next data point to arrive, and you are not doing anything. And if it is less than budget, there will be queue of the data points with waiting for processing. So, I mean, applications, there are many applications. I've already discussed one or two. So another limitation of these existing algorithms is the inability to produce immediate mining results. Immediate mining results, so if you require the results at the, immediately, for example, short-term investors of a stock market, so they will be needing mining results immediately. But long-term investors, they can wait for some time to get the results. Okay, so these are the algorithms. They will first process data, and then you take the snapshot of the processed data, and then offline maybe you will be finding the maybe summarization, maybe a classification, whatever task is required to do, that you will be doing. So these are not capable of producing immediate mining results. So these are the two major disadvantages of these algorithms, which are of budget algorithms actually. So, so what can be an ideal algorithm? Ideal algorithm should be that if you have little time, that means you have less time to process a data point, so you should be able to produce fast results, or maybe you may be able to produce or maybe process the data point approximately, or you defer the processing. And whenever you have more time, then utilize this time to improve your result and get the better results. So that will actually solve this problem of budget algorithms. Similarly, in another limitation can be solved with the help of this kind of algorithms. So whenever a request for mining result comes from the user, it should give an immediate result. Maybe it can be approximate result, and improve its quality with increase in time allowance. So whenever you get more time, you can improve on the results. So there are two things. The first thing is the processing of the data points. You can actually interrupt the processing and take the next data point which is arriving and process that, entertain that. And the other one is, while producing the final results, you produce the approximate results, whatever time allowance is given to you, and later you process it for improved results. So how anytime actually helps, to solve these limitations or to reduce these limitations. So they give best possible results according to the available time allowance. So whatever time is available, according to that, whatever best possible result it can produce, it will produce. and utilizes varying inter-arrival rate of data points or transactions. So if you get lesser time and you get the next object or data point to be processed, you defer the processing of previous one, takes the next one, process it, and then take the next one. So, so when you defer the processing, this is called interruption. So your algorithm should be interruptible, and it should be interruptible anytime. So whenever you get a new data point or you get a query for the result, the algorithm should be interruptible and you should do the required, operation, whether processing or producing result. So this is how up to that time it should produce the best results, best possible results, of course. And then refinement, it does these algorithms, they refine the results. That means whatever processing you have deferred, whenever you have time, you further process from there onwards, and you process till you have time, and then again you can defer if it is required. Similarly for the results, and you can improve the accuracy. So refinement, when you do refinement, then how the accuracy behaves with time. So here you can see this is the time and accuracy. So as time progresses, your accuracy increases. So if you want your result at early time, that means you will get some approximate results, and you can further improve these results, and at a later point of time you will get improved results. This is the crux of anytime mining. Now you can apply this concept on any task like classification, clustering, or anomaly detection, frequent item set mining. So I'll take, so we have actually worked on each one of these. In classification, we have worked on anytime setwise classification, which is slightly different from the normal classification. In clustering and noise detection, we have worked, and any class we have designed. This is the algorithm which we designed and published recently. And frequent item set mining, we published 2 papers, which is this big data research. This is a bit of theoretical work which we have done to prove that what we are doing is, can be proved and results are authentic. Okay. So I'll talk about today maybe set-wise classification, and if time will permit, I'll also talk about frequent item set mining, that is NEFI. So let me talk about first set-wise classification, which is actually different from usual classification. So here the classes are associated with the groups of objects, not a single object will be classified in a class. So group of objects will be classified in a class which are actually belonging to one entity. So each group is treated as an indivisible entity. So that means there is an entity, and each entity produces the objects, and these objects, once you receive this set of objects, then you classify this entity in a class. So class inference is through study of overall distribution pattern of the objects in each entity. So how the objects of this entity are distributed, based on that we will be classifying that entity. single object provides very little information. So I'll give you one example. Maybe we can take the example of tweet feeds. So users they tweet, right? So each user may tweet many many tweets can come from a user, right? So and these can be of different types. One user may tweet on politics, maybe on sports, or maybe different uh, subjects. So the according to the distribution pattern of these tweets of an entity, that entity will be classified. Single tweet may not give you a very or I should say the single tweet may not give the user behavior, right? So here you can see that there are two type of objects, circles and crosses, and they belongs to two entities actually. So can you differentiate the distribution of these two type of objects, circular and crosses? So you can see that crosses are more, on the outer side, and circles are inside, this box. So there is a specific pattern of these crosses and circles that maybe define the class of the these entity whose objects are belonging to cross and circle. So the example which I was talking about is the community detection using text feeds. So these are the tweets from different users or different entities, and tweets are data objects, entities are users, and group of users will form a community. These can be political communities, these can be different interest groups, or any other type of classification. Okay, so actually you classify entities based on the data object distributions. So these tweet distribution, you classify this entity. I hope this is clear. If you have questions, you can ask. Okay. So setwise incoming stream, if we say it is like this. So y1 is d-dimensional data point, which is a tweet maybe in this case, it is a data point, and entity ID. So this data object belongs to this entity, and it's the training data, then label or the class will be known to you of this entity. And if it is a test data, it will be -1. So that's how the incoming stream you will get, and based on the training data, you train your model, and the training will be updated while you also test the incoming data points. So your data stream will be mix of labeled data and unlabeled data. So labeled data, using labeled data, you can update your model, and unlabeled data will be labeled using the model. So this will work. This is actually a stream model. Originally, we have given its anytime model. Okay. So let me just describe how the classification model works for setwise. So there is a model M in setwise classification, and each class has multiple profiles. So this is a class profile 1 to class profile 2, and there can be many class profiles from one class, and there will be many classes, C classes, and total P class profiles. So depending upon the size of the class, you will be having profiles. So if you have more number of entities, a big class, then you will be having more profiles in that. And if you have less number of entities, then you will be having less number of profiles. Okay. So you have entities, class profiles, and the classes. And these are the training entities D11, D12, and D1K. So for these entities, you know the class. And you construct class profile, and which you can update and which you can use for, classification. So to get the class profiles, you first construct entity fingerprints. And for that, you choose anchor points from the data. So these red points, which are given in this picture, are anchor points. And then you construct entity finger points by assigning objects to these anchor points. So you can assign using clustering, or you can assign um, using nearest anchor point, whichever way you want to. I have done using clustering, so I cluster the data, and we get these different clusters for around each anchor point, and these will form, so this cluster will form one class profile. Similarly, others will form fingerprint, entity fingerprint, like this. So this is fingerprint vector for an entity. So for all entities, you construct fingerprints. And from entities fingerprints, you construct class profiles. So this is the model. You have entity fingerprints, you have class profiles, you know which entities they form a class profile, and that class profile belongs to the class. And so whenever a training object arrives, then you can update these class profiles and entity fingerprint first, and then class profile, and then you classify. Am I going okay, or you have any questions?
Yes,
Seems
yes,
go ahead.
yes, Poonam, go ahead.
Okay, okay. So that is how the fingerprints are updated and class profiles are updated. Once you get the training object while entertaining the stream. So first fingerprint, and then class profile. So whenever test entity so how the testing will be done? Because if you think that data object is an object which belongs to one entity, and this single point, using data point, you can data object, you cannot classify an entity. So you have to wait for some data objects to be collected from an unknown entity whose class is not known, which you want to classify. So you wait for that, and once you get the entity fingerprint, unknown entity fingerprint, and then you scans the class profiles and see to which class profile it is close enough to classify that to that class. So you can do it by 1NN. So 1NN is the nearest neighbor, first nearest neighbor. So you match the entity profile with the with all the class profiles and then see which one is the closest, and then you classify that, test entity as the class of the closest profile. And this is done in order of P time. So P number of total profiles. So you need to, actually compare your entity fingerprint to all the profiles. Okay. So how we have modeled this problem in any time fashion. So our algorithm named as NESC, any setwise classification, and we use a data structure called CProf tree. So we actually use forest of C class profile trees, and each tree we name as CProf tree, and is similar to R tree. R tree is a spatial indexing structure which is used. The CProf tree is actually similar to R tree. So that means it is a spatial arrangement. What R tree does, this tree also does the same way, the spatial arrangement of data objects. And it is a balanced tree, and the searching time is order of log n. Okay. So CProf tree is basically fingerprints are at the leaf nodes. So bottom up construction as you do in R tree, bottom up construction of CProf trees. And you may intermediate nodes, they represent the profiles. So this is the hierarchical class profile arrangement. So in the original SC work, they used the flat structure. For any SC, we have used hierarchical structure to arrange the class profiles, and all these internal nodes are basically class profiles. And whenever you get new training data, you update this tree. So this is a CProf tree for one class. There is one CProf tree, right? So you have 20 classes, then you will be having 20 CProf trees. And the entity, training entity, the class label. So you go to the appropriate, prof tree, and then you update that. So how the update will work? So when the training data will come, you start with the leaf node, that is the entity profile, and update all the nodes till the root. So that means to handle a training data point, you need to update these many nodes. Now here the anytime concept you need to bring in. So if you do not have sufficient time to process all these nodes, so if time expires before update completes, so that means your algorithm of updation should be interruptible. That means you should be able to interrupt in between and then take the next data point and then update again. So for that, suppose you start from here and here your time allowance expired. Still you are left with 2 nodes to be processed. So what you will be doing, you will defer here. So interruption means interruption will, if new data object will come, your algorithm will be interrupted, and it is interrupted anytime. So there are two type of operations we have defined. One is the primitive operations, which cannot be interrupted. So suppose we are updating a node. Here the updation of a node won't be interrupted, but you can interrupt the processing of these many nodes. So update the tree can be interrupted. So after these three nodes updation, suppose your time expired, then you interrupt and you store this deferred insertion, you can say, deferred insertion here, you store that. And whenever time will be available, you will process from here. Not only you process from here, suppose you get another update. You interrupted here, it is waiting here, and then suppose you get updation here at this node. Then you update from here and you have to go this way, right? Then whenever you pass from this node, then you take this update along with it and then update. So while updating the other one, so this concept is called hitchhiker. So you use a hitchhiker to, to take that along with this updation, the second updation, and update all the nodes. If you have more time, if you do not have time, suppose you interrupt here again, then that update will also sit here, and then the next data point will be taken. So in this way, whenever you update and you check whether there is someone waiting at that node or not, if it's something is waiting to be processed, then you take this along and then you update. And as I told you that in real time applications, there is the time allowance or the inter-arrival time is different. So whenever you have more time, if your updation is finished here, then you check for the next updation wherever in the tree the something is, suppose residing here or something is residing here, then you take from here and then update. So we use for storing these buffers, and if the buffer is full, then we need to remove the weakest update. So in stream models, sometimes we use damped models, sometimes we use sliding window or maybe a tilted time window. So if it is a damped window, then the older transaction or data points will fade out, the new ones will have more weight. So if the points which are residing in buffers, they will either fade out. If they won't be they will be having some weight to that, then we'll remove the weakest data points from the buffer to maintain this, the space constraint. So and that's how the approximation, is introduced in the algorithm. So this is handling training data objects. Similarly, the testing time also, we have written the interruptible classification test algorithm. That is, we do actually best first traversal on all CPROF trees. Best first traversal is actually takes into account all the root nodes of the CPROF trees once the entity fingerprint you get, and you choose the k nearest nodes to that fingerprint to move further. So suppose you choose 1/5 and ninth C prof tree whose are close to the fingerprint, then we take the the profiles, next level profiles of the C prof tree, these C prof trees. So we'll take, suppose this node is closer to the entity, which is test entity, then you take all these nodes so you keep all these in a priority queue. So first you keep all the root nodes of the C prof trees, suppose m number of C prof trees. So you take you m number of root nodes you insert in the priority queue, and then you take the first k profiles which are close to the entity fingerprint, and their sub next level profiles you take and insert in the priority queue, and then the best k again, and then so on. Keep on doing this. You will reach to the penultimate nodes, and then the closest profile will be the classification. I mean, the class of the closest profile will be given to the test entity. And this is also interruptible. So if time allowance is less, you refine your search space till that time, right? So if time allowance is less to provide the result, then whatever level up to you have reached, you use that to produce the results, and probably those will be approximate result. And whenever you get more time, you can, next time you can actually classify that entity again and get the better class. This is about NESC. Some of the salient features of NESC: the flat structure is replaced by hierarchical structure to handle variable interarrival rates. Um, it gives you high classification accuracy at the low speeds. Efficient in incremental updates. So multiple updates are merged together, and that's how you better, get the better accuracy, because the updates you can have more updates you can actually handle in one go. And efficient class assignment and class profile construction, and this is parameter free, so we do not need actually I should not say parameter free, because you decide some fan out for the tree, like in our tree you decide the fan out. So but that is, you can have it's not very constrained parameter. You can have more number of class profiles than in a flat structure you can have, because that will be directly proportional to the cost. But here in hierarchical, the cost may not be increased that much if you increase the fan out. I mean, it will increase, but it's not linear. Anything at this point? Okay, so the another thing which we have done is NEFI, that is anytime frequent item set mining. This is also based on the same concept, anytime concept. So let me a little bit talk about the frequent item set mining, which has two approaches, majorly a priori based and FP growth based. A priori based, where you find first one item sets and then you generate two item sets and three and so on. And FP growth, you build the FP tree and you mine this FP tree whenever you want. So, I mean, so basically, frequent item set mining, uh, they run around these two type of techniques. In stream, it is very difficult to have a priori based techniques, like because you will be you have to update first one item set, then two item sets, then likewise. So that, and it's a multi-pass algorithm. And as I said, for streams, multi-pass algorithms are not suitable, because this the speed of a stream is too high to see the data again and again. So that's how a priori based algorithm, if people design, they design for sliding window. So window size you can keep according to the space available in your machine, and otherwise, mostly FP growth based techniques are applied in for streams, where you construct tree and you update tree in online fashion, and then whenever you get a query or you need to find the result, you process this tree for mining results. So basically, these are the two approaches which are used. So our idea was to do something in between, because a priori based approach is space consuming, space is the constraint, and FP growth is basically takes lot of time to mine, because FP tree mining is time consuming. It takes a lot of time to mine. So basically, you are processing data points maybe quicker than a priori based algorithms in FP growth type algorithms. And if you go for a priori based, you are consuming more space, but results can be obtained quickly. So we have done something in between, as I said. Um, it's not fully FP tree type, it's not fully a priori type. So here we have constructed BFI forest. So this is consists of BFI trees. So you can see that this is the structure of BFI forest. It consists of the number of trees. You have unique items in your data set. So here you can see that this tree is a top-down tree. Unlike in Setwise, that was a bottom-up R tree type of structure, here it is a top-down tree. And this tree, suppose your transactions are consist of A, B, C, D, E, 5 characters, and you will be having tree which starts with A, tree 2 which starts B and C and D and E, right? Then all the transaction, the idea is all the frequent item sets which starts with A can be mined from only from one tree, which is this. All the frequent item sets which starts with B can be mined from second tree, and so on. So unlike FP tree, for mining the item sets from the FP tree, you have to mine the whole tree. and it's a very big single tree. But here we uh, actually divided the processing into several parts. So as many parts as the unique items you have in your data set. So any item set, suppose ACD, you will get from only from this branch. This item set you will not get from any other branch. This is the main, actually it's the beauty of this tree, and there are so many terminology which you can see here. So we keep many, parameters at each node, like frequency count of an item set. So frequency of internal node, any frequency at internal node gives the frequency of that item set. Suppose at C you have 2. That means AC has 2 frequency. FTID is the transaction ID when the node first created, and so on. There are so many things, and buffers are used again for wait to wait the transactions at a node which are to be updated in the tree. So tree will be updated each time whenever you get a transaction, and again there will be primitive operations and interruptible operations. Will define what are the primitive operations and what are the interruptible operations. But here buffers are only kept on couple of two levels or 3 levels at the most, depending upon the statistics of your data set. And we keep at the external nodes, we keep FP tree. So these are the FP trees, right? And buffer is a buffer structure is like a hash tree, hash table of this kind. I'll discuss more here. So suppose you want to insert the transaction CDE, ACDE, ACDE, is right. So the transaction which is to be inserted, that is ACDE, CDE. All right. So the first, so this transaction. So first of all, this transaction is will be so you will be constructing prefixes of this transaction, like CDE, DE, and E. So these are the postfixes of this transaction, CD, DE, and E. So that means CD has to be inserted in the first tree, and DE has to be inserted in the tree, this tree, and E has to be inserted into this tree. This is tree for A, this is tree for B, C, and so on. Okay, so that's how you need to insert in the tree. So the primitive operation is that you insert CDE here in the buffer of the tree 1, DE in the buffer of root node of tree 3, and E at the root node of tree 4. So the idea is that you don't insert the whole transaction in the tree, like in FP tree or like in a priori based algorithm, that you find all the subsets and then see where to fit them. So you postfix, you insert, and so this is a primitive operation that postfix, all the postfixes are to be inserted into the tree, and you keep them in buffer. You don't do anything, and buffer structure is used to, to to keep them. And then if time is remaining, then what you will do, you will take on some heuristic, you take the transaction from the buffer of the root node and insert at the second level of that tree. And it will be same operation at the second level, at this level, as you have done here at this level. The same, because DE you have to insert here and E you have to insert here. So you will only insert DE here and E here, and that is a primitive operation. So interruption can happen either after inserting the first level, after inserting the second level in a tree, or after inserting the third level, and so on. And these are very, unit time operations, inserting CDE, these postfix in a buffer. And so, I mean, you will get a very nice, efficiency using this approach. So these, all the insertion is interruptible. Okay. So likewise, you actually insert and update the tree, and whenever you need to mine, so I'll just skip all this. And whenever you want to mine these trees, you can, you have to traverse the tree, nothing else. No operations are required, only traversal is required. And when you traverse the tree, you will get all the frequent item sets. There are a few things which are very important to this algorithm. I think I missed to, add the slide for that. So there are some techniques which are used: intermittent pruning, theta buffering, and maybe there are more, like, just to give you the idea, buffer pruning, theta deferring. So buffer pruning, how to prune the buffer whenever there is a, more number of items to be inserted when the buffer is full. Theta deferring, intermediate pruning, all these are the, an FP tree height, how to, what height FP tree is suitable to get the efficient results. So we make both traversal of the tree and the, that means mining, getting the frequent item sets, and insertion in the tree, both interruptible. I think this is the main idea of any time insertion and, finding the results. You can check out papers for more detailed, uh, you know, results and more detailed discussion. This is all from my side. If you have questions, maybe I'm happy to take.
Hello, Poonam.
Yes. Yes.
So when you say approximate, so approximate is compromised accuracy in terms of
Yes, it
classification?
will be compromised accuracy. So approximation occurs when your stream speed is very high, and and you keep on, buffering your items, either transactions or data points, and you don't get time to refine more. Then when your buffer will be full, then you need to remove something from the buffers,
So, I mean,
right?
No, that is fine, but see, the approximate algorithms I mean, it's
So in
already
that case, yeah,
established term.
accuracy will be compromised.
So it is an established term in literature, like what are approximate. So I think
Yes.
if we just say compromised accuracy, that would be much better.
Better.
Yeah.
Yes, it is compromised.
And just one quick question on, so for any time algorithm, there is no idle time. They are all the time working. Is that
Yes,
true?
yes, all the time working until unless you have fully inserted everything.
Okay.
If your stream speed is really slow, then you don't need, to wait, you process every point at the time, or maybe along with other items at process, item data points processing, and you are done with all the processing.
So it will sit idle only when there is no work.
No work to do.
Yeah. Okay.
Then I guess there is no question. So what is the next? Stop presenting.
Okay. I think anybody has any questions? Yeah. All right. Thanks, Poonam. It's a nice talk.
Thank
Thanks.
you.
Thank you. Bye-bye.
Bye-bye.
Yeah.
Thank you, everyone. Yeah.